Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CIC, Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the graph concepts and then BFS algorithm. So, in graph is nothing but a function, or it may be denoted as sometimes as a line graph, bar graph, but this and all not be considered. So, the graph is entirely different one. So, here the elementary mathematics. So, the graph should be refers to a function, a graph, a graph of a function that is nothing but a plot. And as used in graph theory, so the term the graph does not refer to the data charts such as line graphs and then bar graphs. So instead that, so it is going to be refer a set of vertices, so that is points or nodes and edges and lines that going to be connect the vertices. So graph is nothing but a visual representation of edges and vertices, and edge is nothing but the line between the two boundaries, and vertex is nothing but a point where the two or more lines okay met together. So that is should be vertex here. So in elementary mathematics, so the graph is able to refer to as a functional graph or a graph of the function. So that is nothing but a plot. And as used in graph theory, so the term graph does not refer to data charts, okay, such as line graphs and then bar graphs. So instead, it is going to be referred to set of vertices. So that is nothing but the points and the nodes, and edges is nothing but the lines that connect the vertices. And so the graph is nothing but the visual representation of edges and vertices, and the edge is nothing but the line between the boundaries, and vertex is nothing but a point where the two lines meet. And so this is the representation of the graph actually. So here these are the points, so that one is going to be represented as vertices, and like A, B, C, D, and the edge is going to be represented as A, B, B, C, and then A, D. So these and all will be the edges here. Okay. So edges is this one in this one. So this should be the three-dimensional diagram. So where these points are going to be represented as the vertices here, and these and all will be the edges here. Then comes to different types of graphs. So we are going to have different types of graph: multi-graph, simple graph, and pseudo-graph. So what is this multi-graph here? So the multi-graph is going to have the multiple edges and are going to be allowed between the vertices. And simple graph is nothing but a graph without the loops, and with at most one edge between the two vertices is nothing but a simple graph. So unless stated that, so the graph is going to be assumed to as a simple graph. And the pseudograph means that the graph which may contain multiple edges and graph loops is nothing but the simple graph, multi-graph, and then pseudograph. Okay, so the multi-graph is nothing but the multiple edges are going to be allowed between the vertices. So that means this is the example of the multi-graph. So here we are going to have the vertices like this. So in between the vertices, so if you are going to allow the more than one edge, so then it should be called as a multi-graph here. And simple graph means that, so the graph without the loops and then at most one edge between the two vertices is nothing but a simple graph. Okay, example this one. So these are the set of vertices, and in between the vertices, so there is no edges present between them. So that's why this should be called as a simple graph. And the pseudograph means that a graph that may contain multiple edges and graph loops. So this should be called as a pseudograph. Okay, so a graph that may contain multiple edges and graph loops, this should be called as a pseudograph here. Okay, so these and all will be the different types of graphs, and the simple graph should be in terms of edges and vertices. So let us consider a graph here. So this graph is going to be represented directed graph and undirected graph. So the graph what is going to show here, this should be unlabeled graph. That means I'm not going to be represent any kind of vertices and edges here. That's why it should be an unlabeled graph. And second one, what are going to have the edges is going to represent, that's why it should be edge labeled graph, and then the vertices what I'm showing that should be called as a vertex labeled graph. So these are the other types of representations of the graph. So where the vertices is going to be represented. So unlabeled graph, and then edge labeled graph, and then vertex labeled graph. And the graph coloring is another concept in this graph theory. So the graph coloring is nothing but the assignment of labels and colors to edges or the vertices of the graph. So that should be the graph coloring here. Yes, okay. So if I'm going to consider this, so along with this, we are going to have one more types of graph. We are going to see that should be undirected graph is the one thing. So that means, so this is one undirected graph, and whenever I'm going to represent edges with directions, then it should be called as a directed graph, and this one what we called as a undirected graph, right? So the graph where the edges are going to be where the edges are going to be represented in the form of directions, so then it should be called as a directed graph, and uh, the edges which is not going to show any kind of directions, then it should be called as a undirected graph. So the graph coloring should also be done based on the different types of graphs, like directed graph as well as undirected graph. So that mainly this graph coloring is that, so the assignment of labels and colors to the edges and vertices of the graph is called graph coloring. So there are two most common types of graph coloring. So first one is that edge coloring and vertex coloring. And this edge coloring means that, so here I'm going to take assignment of labels and colors to each edge of the graph such that the adjacent edges must receive the different color. Okay, edge coloring means that assignment of labels and colors to each edge of the graph such that the adjacent edges must receive the different color. And vertex coloring means that assignment of labels on the or each vertex of the graph such that no edge is going to be identically colored vertices. This should be the vertex coloring of the graphs. Okay, so edge coloring means where we are going to assign the colors to each edge of the graph such that the adjacent vertices must receive different colors, and whereas this vertex coloring means that, so here the graph is going to have the different colors, different vertices in such a way that no two vertices is going to have the same color. Okay, so let us consider this is the graph what I'm going to have. Suppose if I'm going to label with red of this one, I'm going to color as green. So not two vertices is going to have the same color. So when I'm going to map this as the green, so then I can able to write it as red, and similarly I can able to write it as green color and red color. And if I'm going to assign the green in this case, so what will happen? So this vertex and this vertex is going to be coincide. So that's what I'm going to say. I'm going to assign blue here. Okay. So the chromatic number of the graph should be 3. So three colors are needed. So first one is red, blue, and then blue. So here, next one. So what is the basic concepts of this? So the graph is nothing but a collection of vertices and then edges. And these vertices also called as the nodes, and edges is going to be called as a link. And some different types of graph, what I said previously is that, so the undirected graph and then directed graph. What is the undirected graph? So the edge consists of set of two elements such that the edge UV should be same as DU. Okay. So in this case, so I'm going to have a graph like this. So V2 V1 and V4. So this V1 and V4 should be same, or V4 and V1 should be same. Okay, so then I can able to say these two. Then I can able to say that should be the undirected graph. So whenever the edge V4 and V7 and V7 V4 may not same, then I should be called as the undirected graph. Okay, so let us consider this. So V4 and V7. So this both are same. So if I'm going to give the directions like this, so V7 and V8. So V7 and V8 is not equal to V8 and V7. That's why it should be a directed graph. So I'm going to have the complete graph, that kind of that. So that should be whenever there exists an edge between every pair of vertices, then at that the graph should be a complete graph. Suppose if I'm going to draw the direction from vertex V1 to V2, V3 and V4. So similarly, I have an edge. So V2 to V1, V1 to V3, and V2 to V4. Similarly, I'm going to consider V3, V3, V1, and V4. So I'm going to consider V4, V1, V4, V3. So the graph is said to be that. So if there is an edge between for every pair of vertices, then I can able to say they should be the complete graph. So what is this directed graph here? A graph is said to be directed such that E should be set of ordered pairs, and even if you are going to have edge UV is present, then edge V2 may be absent. So E is nothing but set of ordered pairs, and if I'm going to have the edge UV is present, then edge V is may be absent. So the directed graphs are going to be drawn with the nodes for the vertices and arrows for the edges. So in a directed graph, so the edge vertices are going to present the form of the nodes, points, and vertices, and where this should be the directed edge is going to be there in our directed graph. Let's see some of the terminology in the graphs. So what is this adjacency here? So the vertex W is said to be adjacent to V if and only if the edge VW should be present in that edge set. So weight is nothing but the cost parameter that is going to be associated with each edge. And the path is nothing but the sequence of vertices W1, W2, and so on Wn, where there is an edge for each pair of consecutive vertices. Okay, a sequence of vertices W1, W, so on Wn, so where there is an edge for each pair of consecutive vertices. And the length of the path is nothing but the number of edges along the path, and the length of the path of n vertices will be n minus 1. And the cost of path is nothing but the sum of the weights of edges along the path. So adjacency means a vertex W is adjacent to V if and only if VW is in A, and the weight is nothing but a cost parameter that is going to be associated with each edge, and the path is nothing but the sequence of vertices W1, W2, and so on Wn. So where there is an edge for each pair of consecutive vertices, and the length of the path is nothing but the number of edges along the path, and the length of the path of n vertices should be n minus 1. And the cost of the path is nothing but the sum of the weight of edges along the path. So the length of the path is nothing but, so the number of edges along the path is nothing but the length of the path, and the length of the path of n vertices is nothing but n minus 1. So here the cost of the path is nothing but the sum of the weights of edges along the path. And representing graphs, so assume that V is equal to V1, 2, and so on, and the adjacency matrix represent the graph as n by n matrix. So A of I comma j should be 1. So if there is an edge, that should be belongs to edge E, and that should be 0 if there is an edge below does not belongs to. Okay, so we are going to have the vertex at 1 to n, and then adjacency matrix is going to be representing the graph so as n by n matrix. So the edge aij should be 1, so if there is a edge belongs to E, and 0 if the edge does not belongs to E. So next one is adjacency matrix. So here what I'm going to say that is, so adjacency matrix means that, so we are going to have the graph like this, how the graph is going to be presented. So adjacency matrix means, so what are the vertices is there. So what are the vertices are there? So all the vertices are going to be represented in the form of rows and then columns. So whenever there is an edge between them, so I'm going to represent it. So 1 to 1 there is a no edge, so that's why it should be 0. And I have an edge from 1 to 2, so that's why it should be 1. Then I have an edge from 1 to 3 and 1 to 4, 0. Then again 2 to 1, 2 to 2, 2 to 3, and 2 to 4, 0. 3 to 1, so 3 to 1 is there, so no edge. 3 to 4, there is no edge that is going, and 4 I have 4 to 3, so remaining should be 0. So like this we are going to be represent the adjacency matrix representation of it. Then adjacency list means that, so here the graph can also be presented in the form of linked list. So for that what I'm going to say that is, so if I'm going to consider one vertex here, so that should be as one node, and what are the edges that are connected with this vertex is 2 and then 3. So similarly if I'm going to consider 2, so what are the edges that are connected? 2 to 3. For 3 there is no edge, and then 4, 4 to 3. So like this you are going to be representing the linked list representation of the graph as well. So in adjacency list, so for each vertex we store a list of vertices that should be adjacent to it. So adjacent to 1 is 2 to 2, and this should be 9, and 4 should be 3. So the variation can also be keep a list of edges coming into vertex. So then graph searching. So graph searching means that, so the graph may be directed and indirected, and the goal is that, so methodically explore every vertex and every edge. That is the goal. That means we are going to be check whether the particular vertex is present in this graph or not, and how to find it out. So for this, we have what we call as a graph search. So ultimately, we are going to build the tree on the graph. So pick up a vertex as the root and choose the certain edges to produce the tree. Okay. So pick up a vertex, so as the root here, and then how to choose the certain edges to produce the tree. So what in that we are going to see what should be the breadth first search. So breadth first search is nothing but, so we're going to be explore the graph and turning it into a tree. So for that first you have to one vertex at a time you have to use it and expand the frontier of this explored vertices across the breadth of the frontier. Okay. So build the tree over the graph, so such that you have to pick up the source vertex to the root and find its children and their children again. So explore a graph such that we should be turned it into a tree. So for that we're going to take one vertex at a time, and then we have to expand the front area of explored vertices across the breadth of the front area. So build a tree over the graph such that we have to be pick up a source vertex to the root, and then next we are going to be find the children and then children again. So breadth first search means, so here I'm going to solve by making use of these colors. So for this, I have to be color the vertices. So how the work algorithm is going to be work. So for that, I'm going to consider white vertices, gray vertices, and then black vertices. So white vertices means that they have not been discovered. So all the vertices start out white, and gray vertices have to be fully discovered but not fully explored, and black vertices are discovered and fully explored. Okay, so the white vertices what I'm going to consider that has not been discovered, and gray color vertices means that so the vertices are discovered but not fully explored, and black vertices is nothing but discovered but fully explored. So all the vertices are going to be stand by the using of adjacent list. So let us consider a graph here. So in this graph, what I'm going to say that is, so first of all, I have to mark the infinity to all the vertices of the graph. So then what I'm going to say, so initially I'm going to take the source vertex. So that vertex is going to be pushed onto the cube. Okay. So initially I'm going to consider one source vertex. So that vertex is going to be pushed onto the cube. So initially mark it as S. Then after that, so whatever vertices that are adjacent to S, that one I'm going to be C. So for S, so whatever the vertices that are adjacent, so R and W, so those two will be pushed onto the Q, and S is going to be deleted. So next we have to find, so what are the vertices that are adjacent to W? I have to find. So for this W, I'm going to have um, T and X. So T and X I'm going to be push onto the Q here. So initially RW, so for R S and then W is going to be taken out, and then what are the vertices that are adjacent to W is going to be pushed into the Q. And then next one, so we have to find what are the vertices that should be adjacent to R. I have to find, for that V is there. So V should be pushed onto the Q. So for V, so for R, so what are the vertices that are adjacent to R that should be V? So T, so S, W. So these three vertices were visited. Then once that one, so again I have to consider T in this case. So for the T, so what are the vertices that are adjacent to T, U and X? So U and X is going to push on the Q. So what is to be done? So U and X is going to be pushed on to the Q. So for T, what I'm going to say U and X and V is there. So from T again I have to find out, so what are the vertices that are adjacent to X is that Y. So Y is going to be pushed onto the T. And then V, so V there is no adjacent vertices, the leftover vertices U and V. So V is also visited and Y also visited, the Q is on there, and this should be the resultant bed first search, right? So once again I'm going to explain this. So bed first search uh, is nothing but we're going to explore the graph where the graph is going to be turned into a tree, and further we're going to be build a tree over the graph and pick up the source vertex to the tree. So here what I'm going to consider is that, so we're going to consider three types of vertices: white, gray, and then black. And from this graph, initially I'm going to mark all the vertices. I'm going to consider this should be as a source. So, and from this, I'm going to find out what is the vertex that should be adjacent to S. So, that should be R, and W is going to push onto the Q. Next I'm going to visit W. So for the W, what are the vertices that are adjacent? That should be P and then X. Those things I'm going to push onto the Q. And the next is R. So what are the vertices that are going to be adjacent? V. And from here again I'm going to see U. So this should also be considered. G, that's the vertices used. And next I'm going to consider X here. So for the X, what are the vertices that are Y? So next I'm going to visit B, U, and then Y. So this should be the BFS order of this graph. So similarly, if I'm going to consider one more graph like this, like A, B, C, D. So we're going to be trace out the BFS means. So first I'm going to be started in this case. So for A, so I'm going to push what are the contents, what are the adjacent vertices that are going to be A, B, and C. So next one I'm going to delete B. So what are the vertices that are adjacent to B? So that should be E and C. C is already there. So E I'm going to push that. And C is going to be deleted. Next C. So for C what are the adjacent vertices? D. So D is there. And for next I'm going to delete E. So for D what are the adjacent? E is already there. A B C. So for C, it should be D. So for C, what are the vertices? D is there. So D is already visited. Next one is E. So D already there. So next one E and then D. So this should be the BFS order of the evolving graph. So let us look at this algorithm. So BFS, so input should be graph and then starting node. So initialize the vertices. So initially I'm going to make as the starting node of those. And when the queue is not empty, so remove the top of the queue. And then for each adjacent, so if V tends to color is white, then I can make V tends to color equal to gray, and V tends to D, and V tends to B. So I'm going to mark and Q onto the Q, and finally I'm going to apply. So this should be the BFS search. So let's see the code again. So in this one, so initially I'm going to consider should be the input graph and then starting node. That should be starting vertex. So initialize the vertices, what I'm going to have, and initialize the starting vertex to Q. So while Q is not empty, so remove the top of the Q. So and then for each vertex that should be adjacent, then you have to take V tends to color equal to white, V tends to color equal to gray, and you have to make V tends to be equal to V tends to be. So that means every vertex that appears in some other vertex that should be adjacent first, and make the color equal to blue. And the total running time of this algorithm should be equals to the fitness.
Like, share and subscribe. Hit the bell icon for more updates.